also in reinforcement learning, you can look at it as a function. So the policy, for example, which we'll cover later, is also a function. So machine learning is a very, very powerful way of approximating functions. So yesterday we saw that there is like a very theoretical result saying that like in theory, any continuous function can be approximated with a one hidden layer neural network. But there were a lot of concepts that are kind of advanced. There was the distance between functions, for example. There are many different ways of defining distances between functions. Are you guys familiar with that? Are you familiar with that? But how to define distance between two functions? What's your background?
I don't think so.
What do you study in general?
Biomedical engineering.
Which?
Biomedical engineering.
Biomedical engineering. Okay. Okay. So, what about you?
Material science.
Material science.
All I know is what you said yesterday.
You were yesterday. Was it clear?
I think so.
Yeah. There are many ways to. If you have two functions, f and g, let's say like this, and we're asking if one of them is approximating the other. So this one of the central ways to define this is using the kind of maximum distance between these functions. Maximum distance. And that's what I did yesterday. And let's assume that all these functions are defined on some set. Let's take just the cube. It's a unit cube. Real valued functions. Hi, I was asking if people have any questions about yesterday, other topics. Okay for you? Right. Okay, so maximum distance, so we call it supremum because in general maybe there is no maximum, but there is like some sort of upper bound. Actually, in case of continuous functions on these kind of compact sets, then this always is a maximum. That's different from saying, so what can we do with this kind of thing? We can use it to say that a sequence of functions approaches some function. So approximation means that we have some data, and then we start approximating it with neural networks. So you start with a simple neural network. Your simple neural network outputs a function like this. It's long. You measure the distance, which could be the error, call it error, whatever. Then you start updating, training. This function goes closer and closer to your data. And mathematically, we want to speak about convergence. So we want to say that the limit of functions, sequence of functions, is that original given function. So what does it mean to say that the limit of functions is some function? Now, you could try to say that, oh, all that means is that at every point, this function approaches that function. At this point, we approach, this point, we approach, But that's a very kind of bad way of looking at it, because you might have this infinite sequence of functions, like this kind of sequence of functions that approaches your data at many, many points, but it's, let's say, overfitting. You could have like this overfitting scenarios where your data is missing some points here, and then your function is you're approximating with the functions like that. It seems to converge at every point, okay, but you missed some points, so now it's exploding. Whereas this kind of maximum norm considers the whole function as a whole. So it kind of cuts, it creates this kind of a neighborhood of the function where all your approximating functions are supposed to be in. So an example of this, so let's define two things. We have pointwise convergence, which is that at every point the limit is the value of the other function at that point. So that's the kind of that one. And then there's uniform one. Uniform convergence. And uniform convergence means that this distance considered globally goes to zero. We take this function and that function, and as similar notation, as I goes to infinity, this distance goes to zero. That's a different way of defining convergence, and that's the one we were using, and that's the one that they used often in mathematics. And this also bounds all the other ways of measuring distance, most other ways. So, for example, yesterday I mentioned that you can also calculate the distance between functions using an integral. So let's say the L1 distance would be the integral between the integral of the difference between these two functions. Kind of an intuitive measure. You take two functions, you look at the area between them, and that's your error. That's your, you can say, two functions approach each other. If this goes to zero, but that is somewhere in between. Is somewhere in between, because here you again can have this situation that you're approaching with functions like that. The integral here is very small, so this looks like it's very close. But it's still better than the pointwise convergence, which really is wild. And the interesting thing about this one is that you can, this actually gives a number, right? So we can calculate this integral, and it's pretty easy to see that this is bounded by the other one, right? Because assuming we are especially on the unit interval whose measure is 1. I don't know if you guys remember those things from high school. But we have any function, and this is a positive function, right? Because absolute value, so it's positive. And we take the area, that function, it will always be bounded by, so what we're doing here is to take the maximum point of that function, and then we're looking at that box. Why is it the same thing? Because in this case, we're integrating over an area which has measure 1. And so the area of this is simply the maximum point. And that's why it is bounding, it is greater or equal than this integral. So now for functions which are defined on this unit cube, we have this nice inequality, which can help to prove things. So yeah, so let's go through some examples just to make things a little bit lighter. I guess yesterday was a pretty heavy lecture. You can watch it in Oulu. A standard example, let's take the function fn is x to the power n. And again, define it just on the 0, 1 interval. And this is always, so n, this will be always a bijection increasing. It looks like this when n equals 1. It looks like this when n equals 2, n equals 3, n equals 4, 5. You can plot it on computer, 6, etc. Always has value 1 here at 1, value 0 at 0. So what does that function converge to? So the sequence of functions, right? So if we look at this, convert this, look at it at every single point separately. If we take a point which is less than 1, then we have limits what is this going to be? Question to the audience. Let's try. So let's take x, for example, half. Yeah. So x is less than 1, and when we take it to a large power, it goes down. It becomes smaller and smaller. And we raise half to the power, and it goes to 0. And any number which is between 0 and 1, including 0 but excluding 1, will go to 0. Okay. And we are on the interval between 0 and 1. So there's one more point we need to consider, and that's the point x equals 1. So what happens when x equals 1? Just 1. Because n, 1 to the power n is going to be 1 no matter what you do. 1 to the power n in 0. Bam. What does it mean? the function that we are approaching is not continuous. So this approaches a function which looks like this. 0 everywhere below 1, and then it's 1 here. So in pointwise, so this is also why this pointwise convergence is bad. Sequence of continuous functions approaches nothing. Well, approaches a discontinuous function. It's not nothing, but it's not in our space of continuous functions. And yesterday we were looking at the space of continuous function, which I denoted like this for n dimensional inputs. And if we were to consider this, then we would be having a problem, because now this convergence or kind of approximation could take us out of this space. And so then mathematics collapses. The results don't work when your approximation takes you out from your space and have to define another space, and you could, but it's easier to work with uniform convergence. So what happens with uniform convergence here? Simply the answer is that this sequence does not converge. This doesn't have a limit in this sense, because actually we can see that the distance between any two functions in this sequence will be quite large. The distance we can compute. Let's try to compute some distances. So let's take, for example, the distance between x squared and x power 3. So two functions like that in the uniform measure. So this is the supremum of this difference. So how am I going to calculate? How am I going to find the largest value here? Well, first, I can notice that this term equal to this, because as long as I'm in this interval between 0 and 1, this x to the power 3 is always smaller than x to the power 2. So this is positive. So taking absolute value, I can take it away. And then I notice that this is the same as just x squared times 1 minus x. So definitely not at the end points, right? So the possible, you have a function between 0 and 1. The possible places for the largest and smallest values are always at the endpoints for continuous functions and at the zeros of the derivatives. Okay, so at 0 and 1, we have 0. If x is 0, this is 0. If x is 1, this is 0. So somewhere in between must be the maximum. Easiest way is to take the derivative. Derivative of this will be I can use the product rule. Like this, right? So first I take the derivative of this times this, and then the derivative of this, which is -1, times this. Okay, and this is supposed to be 0. So that simplifies to this. Again, if x is 0, we already excluded that option, so we can divide by x. assuming x is not 0. So I have 2 minus 2x x. So half of x is 2/3, right? Let me know if I'm making some mistakes. But this goes to the right. It's 2 equals 3x, and then divide by 3. Okay, so x equals this. So what is this then? 2/3 squared minus 2/3 cubed. Again, using this simplification, we got 2/3 squared times 1 minus 3/3. That is 4/9 times 1/3 for. This is the distance between these two functions. Could do probably a more general. We could do a more general one, actually. What will happen if I take n and n plus 1? Am I going to get this equally easy? It's going to be n. So in the derivative, I have n minus 1. Here I have the same thing. Then here I will have n minus 1. Here n plus 1. Wait. Just n. And here I have just n. And then I can divide again by. So
n in front of the. Instead of the.
Yeah.
sorry.
N.
Oh yes.
Yes.
Thank you. So the same arguments with 0 and 1. So the maximum value is not a 0, not a 1. Dividing by x to the power of n minus 1. We have n. We have n x equals x. And we have the same thing actually. N divided by n plus 1. Oh. What happens when n grows? Goes to 1. So the distance between consecutive functions in this sequence are never close to it. So the next one is always almost 1 apart from the previous one. So this is this goes to 1. So that kind of shows that it's not convergent. You cannot converge. The distance between the consecutive ones is always 1, and it's counterintuitive maybe if you look at this picture, but if you zoom in, and if you plot it with a computer or something, you zoom in, you'll see that it's here where the distance grows, or approaches 1, in this close to 1, because that's where the functions, these polynomials start becoming super steep, and so the distance to the previous polynomial is bigger and bigger. Yeah. Let's look at another. Any questions about that?
Can you explain a little about how it becomes the discontinuous function? This is infinite number of polynomials, right?
Here? Yeah, so
The discontinuous.
this one.
Yeah.
Yeah. So maybe I should make it super clear that these are two different ways of looking at it. So in this way, with this sequence does not converge when we look at the soup. When we look at the pointwise convergence, so we look at any point at a time, separate. And we look at where does the sequence converge at that. Then we get a discontinuous function because when x is smaller than 1, then this sequence goes to 0. So if you like basically just you ignore everything that's happening around you, and you're like focusing on that one point, the polynomial, when you take any x smaller than 1, this goes to 0, right? 0.9 to the power 100 is like 0.2, and then that to the power 100 is 0. But at 1, again, ignoring everything that's happening around you, 1 to the power n is always 1. So the limit is 1. So if you look at the limit pointwise, you get a discontinuous function. You have a function of 0 here. That's the limit of every point below 0. But at below 1 and at 1, the limit is 1. So that's a discontinuous function. But if you look more globally, this sequence of functions, you'll see that the next function is as far from any other function as the previous function. So these are two different senses of talking about convergence, and this is often preferred when talking about functions because it's more reasonable. It kind of takes into account what's happening around the point, not only at the point. Yeah. Now we'll look also at the distance between a function, let's say a function, it's a quadratic function, and a linear function. So yesterday we spoke a little bit about that. There will be exercise about this. And suppose p is let's say 3x plus 1 or minus 1. Okay, so that's a function. So what's the distance between f and g? We're looking at the sum of x squared minus 3x plus 1. Now, it looks difficult to compute because you have the absolute value and then you go to different cases. So naively, you will just start splitting this into to find the zeros of this parabola, and then you'll go between those zeros, blah, blah, blah. But actually, we can make like a very simple analysis. This is indeed, if we take away the, if we don't see the absolute value, it is a parabola which opens upward. And depending on this term, this point is going to be between 0 and 1 or outside of 0 and 1. Well, except I take my words back, it is actually complicated. What?
It's 1.5, right?
1.5.
1.5, right?
Yeah, in this case, it's going to go outside. That's true. So in this case, because this is 3, the middle point is, so if we have this general form, the middle point is like that. So in this case, it's 1.5. So it's like there, which means that the parabola goes here. But I'm just realizing that we can't ignore the fact that it might flip because of the absolute value. So if the 0 is between 0 and 1, then it will flip here, and then it goes like that. This function. So then this is actually the minimum, okay, but that's the maximum. Maybe. Okay, so there's a number of cases. If you go through, if you want to figure out what this really is equal to, maybe we can do it. Okay, so we already figured out that the middle point is this. The 0, where's the 0? This case, have the formula. Where's the formula? Is that correct? I haven't seen this formula for something. Yeah.
Yeah, should be, yes. For AC.
So what do we got? 3. So that's 9 minus 4. It's 5. Okay. So that's 3. And not very convenient. Divided by 2. So the plus goes away. It's on the wrong side. The minus 3 minus square root of 5 divided by 2 is probably between 0 and 1, I'd say. So that's definitely not the maximum point. So what we know now is that this function is really like this. It changes direction once inside between 0 and 1. So the maximum, and it goes first from infinity, plus it descends, then it jumps off 0. So the maximum must be either at 0 or at 1. That much we know now. So maximum is going to be either at 0, which is 1, or at 1, which is it's not, so it's actually at 0. Okay. So this is going to be the max. Now, the exercise we will have is that
One, because we are within.
oh, sorry. Yes, you're right. So it's the same. Still 1. Yes. Okay. I give points for mistakes. Oh, send me an email. Yes, so in the exercises, there's an exercise, like actually several exercises leading to the same thing, showing that if you have this parabola and you have any linear function, then we can find actually a number such that this distance is always greater than that number. And the point is that when you have this quadratic function, it's not straight. So if you take a small enough number and you take a neighborhood which is narrow enough around this parabola, then no matter what you do, there's no straight line that can go in because this is curved. So you cannot have a straight line going, which is completely inside of it. And we prove it in the exercises. And this means that this quadratic function has a positive distance to the subspace of this, which consists of linear functions. So you take the subspace of the space of continuous functions, which consists of linear functions, that is kind of, it's almost the same as you know, in R2, you take a subspace, which is a line, and then there's a point outside of the line, which is kind of has a positive distance to every point on the line. So that's the same thing here. The subspace would be the subspace of linear functions. And this point would be the quadratic function, which is kind of far away from all of them. And this way of looking is the functional analysis framework. Is the idea to look at these function spaces as vector spaces. You have dot product, inner product, you have distance, you have norm, and you can speak about subspaces, and then, for example, linear spaces like that, linear functions, but also quadratic functions are only a small subspace here. So if you take, so in the exercises we show that you cannot approximate quadratic function with linear functions, but it's the same thing. You cannot approximate third order polynomial with the second order polynomials. You cannot approximate fifth order polynomials with fourth order polynomials, etc. And this is actually an answer to my question yesterday, because yesterday I said, look, if you have a linear activation function, then the entire network becomes linear, then you cannot approximate anything. But as soon as you put the activation function to be a sigmoidal, suddenly you can approximate any function. And so I said, can you put just any nonlinear function? And you often hear that, oh, the activation has to be nonlinear. Answer is, I realized it last night, No, actually, any polynomial is bad. Like, just like if you take linear function, you get linear function. If you take a polynomial, put it in a neural network, and it has only one layer, if it has only one hidden layer, like the ones we looked at yesterday, then the network will produce a quadratic function. It will produce a function of a polynomial of second order. We can check that. So and polynomials of second order cannot approximate every function. So it's actually quite interesting. It has to be sigmoidal, or it has to be this rectified linear unit. It will not work with x squared or x cubed or whatever. So if you recall our neural network, we have an activation function in the hidden layer. Here we have the sum. Here we have the input. So this function will give us, this neural network will give us the function given by, there are the weights here, A1, A2, AN, and the weights here, W1, etc. So AI sigma of W dot product plus B. Okay, so that's the function you get. That's the one from the universal approximation theorem, which says that if the sigma is sigmoidal, meaning approaches 0 at minus infinity, approaches 1 at plus infinity, then this can approximate any function. If you put sigma is x squared, then this is always this will always just be a polynomial of second order. Because we just get this. You could open the brackets, you can just, you'll see that all you have are at most two variables multiplied by each other. So it's a multi-dimensional but quadratic polynomial. And you can prove in functional analysis that it's a very small subspace. There's a lot of functions you cannot approximate with quadratic functions, just like you cannot approximate a lot of functions with linear functions. And you put any number here, and any polynomial, any order polynomial, then actually cannot approximate n plus 1 order polynomials. It's pretty impressive that you actually can give conditions to this sigma, namely sigmoidal or this kind of rectified linear unit, that enable one to prove that this approximates every function. And then once you have that, then you have actually a lot of functions that you can tell us. Yesterday we saw that from this sequence, so whichever function you have that you can use to build a sigmoidal function from will also work. Okay, let's have a break and come back in 15 minutes. I'm hoping to start already next topic next hour. So see you.
Function, it is pretty similar to the sigma. I mean, 0 before 0 and 1 after.
The step function.
Yeah,
right. Okay, so the step function you cannot use to, let's say, discontinuous, right? So it's discontinuous. So any function you get from it as a neural network will also be discontinuous. It is good for the kind of binary things. So when we have this MAC pool of bit units and this were logical gates, and you can express any binary function. For that, step function is good if you just put 0 and 1s, but you will not because it's constant, it's flat also. There's less richness in it. So if I have a step function in two-dimensional space, okay, I give you an example. So if I'm applying step function in the two-dimensional space, and I put a line here, so now my function will be 1 here and 0 here, and I put another line. Now this is going to be 1 here and 0 here. So if I sum them up, I have region where it's 1, region where it's 2, 1 and 0. These are constant. So now if I go to the next layer in my neural network, there's nothing I can do. I have actually 3 different areas labeled with 3 different numbers. And the next layer in my neural network is like 3 numbers. Thank you very much. Like there's nothing I can do. I can dump these 2 together. Oh no, actually they cannot even separate between these 2. So it's either like, okay, I can give you this area of 1 and separate it from the area 2 and 0. So we get like a non-convex set. Hooray! So that's what we did in the beginning, the XOR function. For the XOR function, it's not linearly separable, so you need to do this stuff. So with 2 layers in a network, you can do it, but that's all you can do. But imagine instead of step function, you have a ReLU, rectified linear unit, which is it's basically the integral of the step function. Now it's much more rich. Now the first one goes, okay, 0, 0, 0, and then it goes like that. And the second one is like this, and then it goes like that. So now it's not 1, 1, 1, it's like this. So here you have level functions which increase like that. Here you have level functions which increase like that. So by level function, I mean that 0, 0, 0, then here you start going up 0.1, 0.2, 0.3. Same here. And then here they overlap, so you sum them up, and now you have level functions like that. And they increase a little bit faster. And now the next layer in the network has something to work on. In the next layer, you can put a neuron, which, let's say, separates at the level 0.3. And you will have a curve going like this. And you separate an area of this shape. Or if in the next layer you say, okay, take me all numbers which are less than, make some linear function. So maybe you can have some that increases as a function. So you can have like a more complex, whatever. So you can play with the next layer in the network gets more data to play with. And so now, okay, I can do this kind of cuts. There is a paper from 2014 where they analyze how these multi-layered ReLU networks can cut out different parts of the space. They get some results about that. Okay, so that's one answer. Another answer is that when you're trying to do optimization, you want to take derivatives. So, okay, so from the step function, that's a very bad function. For derivatives, it's either 0 or infinity. It's like, you don't do any gradient descent. with this. Here, and on the other hand, you can do gradient descent, even though it's not differentiable at one point, but in most interesting points, you have some direction to go to. The sigmoid is also differentiable. In fact, it's smooth. So it's infinitely many times differentiable. But the problem with sigmoid in training is that the so-called saturation phenomenon happens. So this function is constant. So no matter how far you are, the derivative is always 1 or minus 1. 1. Okay. But with sigmoid, if you end up somewhere far away here, even though the derivative is slightly positive, it's so close to 0 that the algorithms will not pick it up and you will get stuck in that area. The same happens here, this area. So you kind of get stuck in those areas, and that I think is one of the reasons why sigmoids are not used anymore much in machine learning, or they have switched to these to rectified linear units. And as we saw yesterday, from rectified linear units, you can build up sigmoid type of function very easily. So adding up to ReLUs like that, you get a function which it looks like this, which is also sigmoid. So that shows mathematically that ReLU is enough for this, because it satisfies this property, so it can theoretically approximate any function. So why not use them instead of sigmoid? But they're better behaving in the actual algorithms, because for this to actually happen is very rare. You don't really get, probably in your machine learning algorithm, a lot of flat areas. It's probably all kind of piecewise linearly build up of these type of areas, more or less. Right? Any other questions? Now, we'll move this. And then we will start a new topic. All right. So reinforcement learning. Is there anyone here who is currently taking Shak's course on reinforcement? No? Or control theory, where she does reinforcement learning. Okay. She's my colleague. We've been working together. And she is now lecturing, so I don't want to, overlap too much, but if you're not there, then we can do something that. Okay, so reinforcement learning is a whole area. Actually, the name comes from before computers. When you train an animal, you can train it either by punishing it, hitting it with a stick, or you can train it by giving it rewards when it does something right. And then it has been noticed that animals actually learn better to give them reward when they do something right, as opposed to hitting them with a stick when they do something wrong. And reinforcement learning is this applying this idea to computers. And Richard Sutton, who is the author of the book that we're using for this topic, he is a big professor somewhere, I don't remember where, maybe MIT, but don't quote me on that. Check that. So he's a big, he's a big name in reinforcement learning. He says that reinforcement learning is like, it's an area almost like any other thing that ends with ing. It's like machine learning, mountaineering, parenting. So he says the same thing because it's both. It's a problem. It's a set of solutions. For those problems, and it's like a methodology of its own and a theory that combines all of these above. Right? So within an area, you have problems, solutions, theory. And so it's differentiated from supervised learning and from unsupervised learning. So we have so far both. Supervised learning is when you train a network based on data. And unsupervised learning is like ICA, independent component analysis, where you just separate clusters from the data, or you find independent components or principal components without any prior training. But reinforcement learning is somewhere in between. It's like none of those three. Really, you can apply. It's interesting. You can apply methods from supervised. You can apply methods, of course, from both of those in reinforcement learning. So, for example, the typical problem in reinforcement learning is to learn to play some game. Computers playing Super Mario. There is no data like labeled. There is no example of a perfect Super Mario player that the computer is trying to imitate. So it's not supervised learning in that sense. It's also not unsupervised because yes, it has to play the game to learn to play it. It's not just blind source separation. But however, you might be able to use both of those in reinforcement learning because you play Super Mario for 1,000 rounds, you collect the data, you put it in a format of nice supervised, neural network type of setup. You train your network in a supervised way, and then you come back and you play again your games. So it's like a mix of those. Of course, maybe on the way you are using ICA to polish your data or something. So reinforcement learning really uses other types of machine learning, but in itself is like a theory which is its own kind of independent component machine learning. Okay. So examples Okay, so basic idea in reinforcement learning, we're looking at interaction of systems. So we have the agent, which acts in an environment. Now the environment is smaller box, but usually, of course, it's a big, it's some kind of big place. And from environment, you get two things. In reinforcement learning, you get observations and rewards. And each time step, for example, or at each move up in the game, the agent gets a reward and an observation. And the agent acts. And so there is a loop. Action, observation loop. This action is produced by something called policy, usually denoted with Greek pi. It's a function that takes the history that the agent remembers. So essentially, it just takes the history of observations and actions, some finite sequence of actions and observations from the past. I also usually add one more observation to the end of that sequence. And then we obtain an action. Right, so what has happened before? What I will do now. Oh, okay, I forget also that in reinforcement learning, you also take into account the rewards. Okay, so the function, the policy, okay, what rewards have I received in the past? What I have observed? What have been my own actions? And what was the last action, last observation, sorry. So then I will decide what is my next action. Examples, chess, playing, other board games. When computers became better than humans in Go, that was a breakthrough in kind of combination of deep learning and reinforcement learning. Also now they play chess pretty well, but chess was cracked already before by different methods, but they also used reinforcement learning type of logic, even though it wasn't really machine learning as today. Then adaptive control, that would be robots that adapt to wind or to temperature, even just like the AC, like the air conditioning, where it adapts to the level of temperature, or humidifiers that control their own output depending on the input, so that there always is this loop. And so the area predating reinforcement learning in mathematics is called control theory. Actually, control theory is a subset of dynamical systems theory. So mathematically, that's where you would look if you want to do the more theoretical stuff. Other examples that Southern brings up in the beginning of his book is animal kingdom. So a gazelle that is born is able to walk within 20 minutes. Very funny because I have a son and it took him 9 months to walk, and everybody considered that to be very fast. They walk in 20 minutes. And how it happens? Well, according to Sutton, and I think he's pretty much correct about that, it's reinforcement learning. Of course, it has pre-adaptations and it has certain muscular and neurological wirings that help it to do so, but it stands on the ground and it gets I don't know, dopamine feedback from stabilizing itself, and the muscular and neurological pathways adapt through this kind of reinforcement learning process to this upstanding. In fact, with humans, it's the same thing. It just takes longer, but it's actually very similar because human babies have kicking reflexes already in the womb, and after they come out, they continue kicking, and then this kicking. That's my observation. I don't know if there's any studies about that, but it's pretty clear that this kicking becomes standing, it becomes walking, because it just kicks and kicks and kicks until it realizes, oh, I can kick downwards. Then it's like it works, and there is like clearly this kind of feedback loop. And when you fall down, it breaks the reward, and kind of a good model. It's a good model. Okay, a robot that is deciding, let's say a cleaning, this kind of cleaning robot that goes around the floor. At every moment in time, it has to decide, am I going to go back to charge, or am I going to clean one more room? What am I going to do? If I go there, it will take time to come back. What if I don't recharge? And that all can be framed in terms of rewards. So if it fails to recharge, it gets a dramatic negative reward. If it succeeds to recharge in time, it has a positive reward. If it cleans the room, it has also a positive reward. Now they compete. And then what happens, and the important part of the whole mathematical framework, is that you do this discounted future rewards, like expected rewards. So that's like the main core of the mathematical theory. Is like the theory of this kind of expected rewards. It's called value iteration. So in all of these things, we have experience, improves performance, meaning you improve your policy, or you have a policy that kind of, the longer your history is, the better it performs, kind of equivalent. In all of those, right? So chess, obviously, in adaptive control, it depends on how good your machine is, but it can improve with experience. It can adapt parameters based on what has happened before, and then it's more adapted to what's going to happen, etc. Okay, and so what is this idea of discounted rewards? So at any given time, the agent receives a reward RT. Every moment in time, some reward comes in. And the agent would operate based off that. So it can try to predict the next reward and then try to maximize it and collect greedily, in a greedy way, this kind of rewards. in real world, it doesn't really work very well. First of all, sometimes you can only get rewards in the end. For example, in chess, you only get reward when you win. Supposedly. I mean, you might also enjoy the game, but let's forget about that. Same with the robot. Maybe right now, in that moment, the charging station is very far, but there's something to clean on the other side. The immediate reward would be higher to go and clean. But in the future, the robot will lose the game if it goes out of battery. So how do we incorporate that? So another example, very kind of common if you ever practice actually reinforcement learning in programming, there is this car, which is here. And the car needs to get to this side. And you're trying to program a computer program that will learn, like without any instructions, to learn to drive here. And the trick is that, okay, it gets more and more reward when it's closer. Yeah, so the distance here will be the inverse of reward. The closer you are, the more reward you get. So a stupid computer program will try to always go up, it will never get there. What you have to do, and the computer program should realize, and the human will realize it pretty quickly, is that you go back, and then you have more momentum, and then you go even further back, and then you get even more momentum, and then you get even further back, and then you get there. But you have to go back. In the middle, you have to go in the wrong direction to get there. So without discounted future expected reward stuff, value iteration, so-called, you cannot get there. So what we do is that we define, now forgive me, I don't remember the notations from the book, but we define some sort of thing where the next thing basically is some sort of average. Let me just put it this way for now. You take your current reward and you add some estimate of the next reward. So now, okay, and this is kind of the same as this. So this is not just estimate of the next reward, but this is the sum of the estimated reward in the next step plus then estimated rewards of the more future in the future states, etc. And then you can solve this as a kind of equation. You know, you take t to infinity, and you can kind of imagine that there is some limit, and you solve it. And basically, the idea is that you get that your expected reward at any given time is kind of the expected reward now plus alpha times expected reward in the next step plus alpha squared times expected reward in the 2 steps ahead. So the further you go into the future, the more you discount the future reward. So if you have a chance to get some reward right now, or next step, it will have a higher impact than if you have an opportunity to have a reward 1,000 steps from now. And the meaning of that is very important, because if you value far future rewards equally as immediate rewards, then you are taking huge risks, because usually in the real world, something that happens in the long time in the future is much more uncertain than something that is happening right now, including your estimation mistakes and etc. So that's why in reinforcement learning you have this kind of discount parameter alpha, which is less than 1, where which you use to discount like this. Mathematical upside is that this sequence converges when alpha is less than 1. So the sum, the geometric sum, basically with some weights, if these rewards are scaled also between 0 and 1. So everything converges, and so we'll have nice equations and theorems about that. It's like, well, we all know about, also even he talks in this book that, immediate gratification versus long-term success or something. So if you're on a diet, you might suffer immediate consequences, being hungry or something, but you're doing it for some longer term reward, which is in the future. And so the discount parameter, how high it is, basically determines your commitment. So if your alpha is very small, that means that you're really discounting. The further in the future, the less important it is for you. A person who has very low alpha, so to speak, takes a loan very easily, because now I get the reward, but I don't care what happens in the future. You don't want to go in any long-term diet or something. You just want the immediate reward. Another person who has a very high alpha might be not living this life. Like, anything I do is just for the future. I'm saving for my apartment. I'm looking for a wife. I'm like, I don't know, just not living the life right now. Too much weight on the other side, right? So the balance is very important. Also in computational terms, it's always like a question how to find the right alpha, so you don't discount your future too much, but at the same time you're not completely invested in something that is happening very far from what's going on. Okay, so here's I'm going to give an example. It's again from the book, chapter 1, perhaps. So he talks about this example of tic-tac-toe. So everyone knows this game. So interesting things, and this is where we see it for the first time, and really why is it not supervised or unsupervised, or any of those classical AI tools. Because the example he gives is that imagine you're playing against an opponent who is not perfect, is a bad player. It doesn't know. Of course, in tic-tac-toe, there is like a winning or strategy or a draw strategy. Imagine that draw is a loss for X. Okay, so take a version of the game where either X has to win or it loses. And you're playing against Zero, who is not very skilled, but maybe plays for the first time or something like that. So now there is no classical decision-making procedure, because the classical game theoretic minimax approach, if you know it, if you don't, that's fine. Minimax means I'm going to play as if my opponent is irrational. He's very smart. Like, I'm going to assume the maximum reward for him for her, and I will minimize my risks. That's basically the minimax idea. And this doesn't work here because if you assume that your opponent is very good, you will play suboptimally, considering that your opponent is actually not that good. You will always make like the most conservative move, just not to lose. But you could have won if you just took more risks in this situation because you're playing against a 5-year-old. So it doesn't work. Another approach, dynamic programming, it's called, or like model-based. That's what people typically do with the computer. You have a model of your thing, and then you analyze it. You know, what you make simulations or whatever. That would mean that you actually know how your opponent plays. You have a model of your opponent. You don't. You don't know how your opponent is going to play. It's kind of random. It's not random. Some skill. You don't know the level of skill. Doesn't work. So Sutton says the best framework for this is this kind of feedback loop, experience gathering, reward estimation. And then you don't need to model your opponent. You don't need to assume that they will gonna win or lose or something. You're just making kind of a labeling of all positions. So here's how the kind of simple version. This is so small that you can actually list all possible states of the world of this game board. In the range of 100, so probably less than 1,000 different positions. So you start by being completely, you just flip a coin. In the beginning, you flip a coin, what you do. And the game branches out. From the first position, there are 9 different positions. Then your opponent takes a move. It branches it into 8 different possibilities. You make a move, etc. And then at some point, somebody wins. Now, before anybody wins, let's say you don't know when anyone wins. You just label all nodes 50-50. You say, okay, so my expected reward here is 0.5, 0.5, 0.5. Now, when you win and you're like, oh, now I know I won, you label this node as 1. So you store that node. You remember that, oh, that node, that was like very positive reward. And you, how he calls it, there's a danger of calling this backpropagation. There's no backpropagation. It has some other name for it, but it's what I showed before. So this reward gets added here, 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 and here with this discount parameter. So here you will have so whatever this alpha times this. So whatever you already have here, some expected reward. So you add to it alpha times this. Let's say R. You add alpha squared R here. You add alpha to the power 3. So that means that now you're here. You already kind of have some expected reward that in the future, 3 steps in the future, you might win. So it's been added to this node. Of course, all the descendants of this node will contribute to the expected reward here. And then also it will, when you are here, you can look at the expected rewards of the possible options. And then you can either select in a greedy way, so you can select the one that has the highest expected reward from your memory, or you can explore and you pick a random move that is not necessarily the highest expected reward. Why would you do that? Okay, so there is exploration. So the classical cognitive science terminology is exploration and exploitation. I think Sutton uses something else. I think he says exploration and then greedy policy. So exploitation means you exploit your knowledge, you exploit your model, you have gathered all these expected rewards. Now every position in tic-tac-toe has a label, and now you can use that to always select the highest possible reward, expected reward. So perhaps after years of training, when you go to the most important competition in the Olympics or something, that's when you do that. You don't want to explore anymore. You don't want to take risks. You just want to play safe, take the highest reward, expected reward moves. But when you're training and when you're exploring, when you want to find out what are the other opportunities than what you have not tried before, you do exploration. And we can show, and maybe next lecture, which is on Thursday at 4. This week, because of the Independence Day, everything is shuffled. I'll show you some simulations of that. But basically, if you never do exploration, you get stuck in certain branches of your game, which might not be very good for you, but you already labeled them. Maybe you won once in a while, and so you accumulated some reward. Now you always go to that branch, and you never try something else. So then you're missing out possibly on some very good opportunities. Yeah, very easily that happens. The next lecture, I will show the example of multi-armed bandit, which is the simplest framework to simulate and see what happens when how much exploitation you have to do. And in this context, it shows that, for example, if you do 10% of exploration, even though every time you do it, you kind of lose a little bit because you're not following the best expected reward, you still on average improve your chances, or you learn faster. And you can see from the graphs what's the kind of trade-off there. Okay, so I think we are reaching the end of today's lecture. Any questions? So I will send an announcement, but in this anonymous chat, Presemo, there is now a poll, which I want everyone to answer, which is about the exam. Just want to know how many people are coming to the exam on 16th of December. How many people want to have it in January instead? How many people are not interested in getting any points for this course? So if you could just go there and answer, it'd be great. And after that, we will have another poll to figure out the date for the January exam. So it's not yet fixed. so there will be like an opportunity for those who can't make it.
So there will be two chances.
Two chances, at least two. Yeah, I think if I should make even third one for those who failed the first one or something. Okay. Have a good day. It's only beginning.